So section 5.2 goes on from 5.1. In 5.1, we were just reducing or simplifying trigonometric expressions. Today, we're going to be verifying identities. So we're going to have to basically do a short, informal proof of why some things are equal to the other. So those of you who have taken trig before, this section is the one where you're telling me step by step what identity you're using each time to make one type of equation end up looking like another. Now on this very front page here, these are some algebraic strategies and hints. We had a few hints and tips on the last section, but here's just some more with a little bit more information. Hint or tip number 1 is to make sure you know those fundamental identities and any alternative forms, which is why I'm having you keep that formula sheet looking part of 5.1 in front of you, because that's what we need to make sure we have memorized. The alternative forms of all of those fundamental identities. We're going to try to rewrite the more complicated side so that we end up condensing it down when we're verifying these. It also helps, and this one I'm going to highlight because I think this is super important. It also is sometimes helpful to express all trig functions in the equation in terms of sine and cosine. So that means if you have tangent and cotangent, you're going to want to change them to the sine and cosine version with the quotient identity. If you have secant or cosine, you might want to change them into their reciprocal identities as well. Sometimes that's super helpful, especially when you're stuck. Tip number 4, usually any factoring or indicated algebraic operations should be performed. So if you notice you can factor something using a pattern that we have, or even just taking out the GCF, we're going to want to do that because that allows us to see different parts of the equation. So I have examples here of different types of factoring. Part number 1 is the difference of two squares. Number 2 is called a perfect square factoring. These are like basically shortcuts, so you don't have to factor like by hand. This is the perfect square sum, perfect square difference, the perfect cubes difference, perfect cube sum. Those are hard for me to say. As well as just good old-fashioned quadratic factoring. So we can take this quadratic version of a trig function and factor it into the two parentheses that we might have. Part number 2, indicated algebraic operations, like perhaps finding a common denominator. Let's highlight those words because that's going to be something we do a lot, finding a least common denominator between two fractions to be able to combine them in some way. So reviewing our fraction rules here, if you notice we want to add sine and cosine that are denominators, that's two separate denominators, they need to have the same denominator to be able to do that. So in my head, the sentence I say to myself, which is maybe not mathematically correct, but I say, what is the sine of theta missing from its denominator? Well, it's missing cosine for them to have the same one. So I multiply cosine on top and bottom. What is cosine missing so that they would have the same denominator? It's missing sine. So I multiply the top and bottom by what it's missing. And then when they have the same denominator, you can just add the tops together in one fraction. Tip number 5, when selecting substitutions, keep in mind that one side is not changing because it represents the goal. So we are only changing one side of an equation when we're verifying an identity. And last but not least, we saw an example of this. Multiplying by the conjugate of the top and bottom allows us to use some of our Pythagorean identities. Again, this is just all of the things we might be doing in the following problems to verify these different trig identities. Doesn't really mean anything to you until we actually try a few problems. Now, when we do these problems, we're doing them like an informal proof, which means every time you do a particular step, you tell me what you did. Okay, in question number 1, we are going to verify that this side of the equation matches this side of the equation. That's what we're doing. We're verifying this identity. So the first thing I'm going to do is I'm going to take this side of the equation and write it in terms of sine and cosine, which means I will take that cosecant of theta in the very front and I'm going to rewrite it as 1 over sine of theta. Okay, so we do that. We actually rewrite it, and because I'm wanting this as some sort of informal proof, I'm going to write down why I did that. The reason is that that was using the reciprocal identity. Yes. That's why it's on paper. Yep. Okay, my next thing is my spidey senses are going off that I have something in front of a set of parentheses. When these were regular numbers and you had numbers in front of a set of parentheses, what did you do with them? Distribute. That's what we're going to do. 1 over sine theta times cosine theta is cosine theta over sine theta. Sine of theta times 1 over sine of theta is sine of theta over sine of theta. So again, all I did was distribute. Now remember, our goal here is to get this side of the equation, which we're working with, to look like this simple side. I knew I needed to multiply by that number in front, by that trig function in front, because I didn't have a trig function in front of the other side. But right here, I can use two identities, or an identity and like a mathematical idea to finish this problem. Cosine over sine, what is that equal to? Cotangent. And then what is sine over sine? 1. They're going to cancel out, and so I get 1. Oh, snap, that's what I wanted. So if I have cosine over sine and I change it to cotangent, that's the quotient identity. So I used the quotient identity, and I also canceled out the sine. That's verifying the proof, because now by working with one side and changing it in some way each step, I now have the left side of this equation happening on the right side of this equation, which is our goal for these types of problems. And we're done. Make sense? Okay, let's try another example, because really the best thing we can do with these kinds of problems is just work a bunch of examples to get it to maybe make sense to us. Now again, we are going to try to get the left side to look like the right side. You could pick the right side and make it look like the left side, but I think that this one is more complicated looking, like there's more going on, so we're going to start with that side. What do y'all's spidey senses want to do first? I agree, because if we notice, we're going to end up with one term, so at some point I need to get these two terms to be one term, so I'm going to distribute. No, not necessarily. I like to hope that the right side is the one that you're moving around, but if the left side is the one that's more complicated, you actually work with the left side. It doesn't really matter. I prefer to work with the right side, just the way my handwriting works, but it doesn't matter. Tangent squared of x plus tangent squared of x, cotangent squared of x. So what did we do that step? We just distributed. What's nice about writing the proof is that when you go back and look at your notes and you're like, what did I do here? You already have it written. You literally wrote down the word of what we did. Okay, let's think about this. What else can we do now to maybe reduce this down a little bit? Let's rewrite cotangent using which identity? We could. What other identity do we have for cotangent? That's the quotient identity that she said. What about its reciprocal identity? What's the reciprocal of cotangent? 1 over tangent. And the reason I want to go this way is because it just ends up being faster. You would not be wrong when you're working your problem if you did it that way. There's always more than one way to verify. Now they would cancel, which is why I wanted to use the reciprocal identity. So the tangent from the numerator and the tangent from the denominator cancel each other out. So the next line of my equation would say tangent squared of x plus 1. Okay, so I know that I'm trying to get this down to one term because the thing I'm trying to get it equal to doesn't have a plus or minus except in a denominator. What is tangent squared of x plus 1? Does that look familiar to us? Yeah, this is secant squared of x. Which identity did you use to do that? The Pythagorean identity, which, by the way, we can shorten that to this Pythag, Pythagorean identity. I get it. Now remember, our goal is to get it to look like this. So I know I need a trig function in the denominator. If I force secant squared to be a trig function in the denominator, that means I want its reciprocal. What's the reciprocal of secant? Cosine. Yeah, cosine. So again, I did cosine, I used the reciprocal. identity. And it's looking good because I have 1 over, and it's one fraction. Okay, looking good. Now, is there a way I can get cosine squared of x to look like 1 minus sine squared of x? Yeah, isn't an alternative form of our Pythagorean identity that cosine squared of x is equal to 1 minus sine squared of x? Oh, snap. So there we go. By at the very end, working with the Pythagorean identity one more time, we can rewrite this function as 1 over 1 minus sine squared of x, which is our goal. That's what we wanted it to look like. I think these problems are really fun because it's just like a puzzle, and I love puzzles. I don't like jigsaw puzzles, but I love other kind of logic puzzles. Questions, comments, concerns before we move on? Because really, we're just going to do a good number of examples in our notes so you can see the different kind of strategies that you might have to take to do these problems, but then you'll have the problems on your own to work on.
Are we ever going to have to do it backwards? Like, they'll give them to us equal and we're supposed to, like, go crazy?
No. I don't think so, because you wouldn't know what your goal is. It'd be kind of a fun exercise, though. All right, for this one, we have secant squared of t minus cosecant squared of t equal to tangent of t minus cotangent of t over sine t cosine t. I think that, again, the right side of this one looks more complicated to me, so let's start working with that one and seeing what we can do to get it to look like the right-hand side. I mean the left-hand side. So the first thing we can do here, I see that there is a plus or minus in the numerator. When there's a plus or minus in the numerator and no plus or minus in the denominator, you can actually take these two common denominator fractions and split them apart. Meaning, I can take the tangent of t over that same denominator, and I can subtract the entire other fraction, cotangent of t over sine of t cosine of t. Again, that's basically like undoing the fact that they have a common denominator, separating them into two separate. So we're going to call that a split step. Once we've split these, we know that we eventually need to get some stuff to start canceling. And when you're working with tangent and cotangent, the best way to get stuff to start canceling is to change them to their quotient identity. So in my numerator for each of these fractions, we're going to utilize the quotient identity to see what happens. So tangent is sine of t over cosine of t, and cotangent is cosine of t over sine of t. Yeah, we've got fractions in our fractions, but all we did was use the quotient identity. Now this next step is going to kind of be extra because we might get good enough at looking at these kinds of problems where you don't need to write them out like this. But especially right now, while this is all new, it's probably helpful to take that numerator and denominator and write them just separated apart from each other. So what I mean by that is, here's the numerator of sine of t over cosine of t, and here's my denominator, 1 over sine of t cosine of t. Do we see how I've just taken those two things and split them apart? I think while we're learning, it's especially helpful to see that, where you have, again, your numerator, and then we don't have to keep change flip because there's no fraction in the denominator. If the denominator had a fraction in it, this is the step you would keep change flip. Otherwise, we're just kind of separating the fractions.
Why are we doing the reciprocal?
What do you mean?
Like, this sine of t over cosine of t.
Oh, why is it in a denominator? Great question. It's in a denominator here, yeah? So I can't just like randomly put it in a numerator. It has to stay in a denominator. But the reason I'm having you do this, and again, this separate step may become extra for you if you notice this from the step above, but now that we have it written like this, what's going to cancel in this first term? The sine of t. There's a sine of t on top, a sine of t on bottom. What's going to cancel in the second term? Cosine on top, cosine on bottom. Okay, let's condense this down a little bit. So we're going to cancel, and we're going to reduce this down a little bit. So this would be 1 over cosine of t times cosine of t, which just means I can write this as cosine squared of t. And the second one, the top all cancel, so that's 1, and then I have sine of t times sine of t, which ends up being sine squared of t. So we multiplied there, or simplified. Ooh, Damani, what are you thinking right now? Yeah, if we just do the reciprocals right here, the reciprocal of cosine is secant. The reciprocal of sine is cosecant. And look at our goal. We were trying to get this to look like this from the beginning. So just by doing our final little reciprocal identity, we can be done with this informal proof. Put the little box, fill it in.
So no matter how many bites that you take, it's just gonna...
Correct, yeah. The work on these problems, like your correct answer, comes from telling me with the steps that you did. Because when you start working these on your own, this is not the only way to do this problem. So you may think of a different way, mathematically correct, to get from start to finish, and that's going to be a-okay. That's why your work is your... So the next question. All right. We're going to be working again just with one side to get this to look like another. Now, for this one, they kind of look the same in complicatedness. So it really doesn't matter which side we work with. And just to prove that to you, we're going to work with the left side this time. We're going to make that left side end up looking like the right side. Okay? Now, I noticed that this left side has 1 minus sine of x in the denominator. And there's nothing I can do to change 1 minus sine of x because the only identity I have that even remotely looks like that is squared. 1 minus sine squared. So what we're going to do is we're going to take this left side of the equation and we're going to multiply the top and bottom by the conjugate of the denominator, 1 plus sine of x. So I'm multiplying by the conjugate. The reason we want to multiply by the conjugate is because this denominator, when you multiply 1 plus sine of x and 1 minus sine of x, that is actually the difference of two squares. So there's a very quick pattern for us to use to multiply these numbers together, or these terms together. If you're like, I don't know what that means, Miss Quigley, it's a FOIL question. It's just going to be longer for you to actually FOIL this than use the actual pattern. The pattern is the first thing squared. What is 1 squared? 1. Then you're going to subtract the second thing squared. What is the second thing squared? Sine squared of x. Yeah, okay, great. Isn't that great? Now it looks like the actual Pythagorean identity, so I'm just going to go ahead and continue to write this multiplied on top since I'm multiplying top and bottom. So that was a multiply using difference of two squares, which I'm going to shorthand to DOTS, difference of two squares. But again, the reason we multiplied by the conjugate in the first place was to get that denominator into one of our Pythagorean identities. 1 minus sine squared of x, what is that equal to? Cosine squared of x. So that was a Pythagorean identity. What are your spidey senses saying can happen now? Canceling, yeah. Now, here's the thing. We've got a cosine in the top, and we've got cosine squared in the bottom. Obviously, this cosine will go away in the top, but what's going to happen to the ones in the bottom? Just one of them, yeah. So I like to mark out the exponent when I'm doing this. So when I cancel this one out, I would end up with 1 plus sine of x over cosine of x. Anybody notice something cool? We're done. That was our goal, right? Don't forget what the goal is. Our goal is to get it to look like 1 plus sine of x over cosine of x, and we've done it. I feel like sometimes with me, I get lost in these problems just doing a whole bunch of stuff, and I've maybe missed the fact that I'm done. So always keep the goal in mind.
No, because I'm looking at the left side, like, I gotta get to the bottom.
Right? No, we just have to make one side look like the other. Yeah. Just 2 more, and then I'll let you work. Okay, you're going to help me drive on this one. Which one do you think is the more complicated side?
Right.
Right side. Okay, we'll work with the right side. If we work with the right side, we're going to make it look like the left side. We need to get this stuff to start moving in some way. What do we think we should do with this problem? Oh, thank you for saying that. We actually cannot separate this one. This plus or minus is in the denominator. We're not allowed to pull apart fractions if the plus or minus is in the denominator. That's like number one thing that people do wrong in math is try to separate things like this, me included. It was the mistake I always made as a student. We can only pull these apart if they have a common denominator, not a common numerator, if that makes sense. So that was a good idea. I was tempted to do that as a student. Oh, I would love to use the Pythagorean identity. The problem is Pythagorean identity only works when there's a minus for 1 minus cosine squared. And we're not squared yet. But what can we do to make it squared? By the conjugate. We're going to do that again. So we're going to take sine of theta over 1 plus cosine of theta, and we're going to multiply by the conjugate of that denominator. Conjugate just changes the sign to the opposite sign, because we want it to be the difference of 2 squares.
So the conjugate is the opposite sign.
Correct, yeah. Keep everything the same, change the sign. When we do this, we get one denominator, and it's the difference of 2 squares. So this time it'll be 1 minus cosine squared of theta, and then I'll have my sine of theta and 1 minus cosine theta multiplied in the top. Now, I'll be honest, on my notes that I'm looking at here on my podium, I actually solved this one differently than you guys are saying, so I'm sticking with you guys because mathematically we've done this correct. But that's cool because now we know multiple ways to solve this problem based on what I wrote in my notes. Okay, what can we do here? Why did we make the denominator look like this in the first place? We want to do Pythagorean identities to eventually cancel. So 1 minus cosine squared of theta, what is that equal to? Sine squared of theta. So I forgot to write my step down here. So this was multiply using difference of 2 squares. And then now we can cancel just like we did in the problem before this. So the sine will go away and the squared from the denominator will go away. This will be 1 minus cosine of theta over sine of theta. Okay, let's take a pause, make sure we remember what the goal is. Our goal was to get this to be 2 terms with a cosecant in front and a cotangent at the back. So now that it looks like this, do you notice that the plus or minus is now in the numerator and we have a common denominator? Let's split that apart by the common denominator here so that it looks a little different. This will be 1 over sine of theta minus cosine of theta over sine of theta. That's my split step. So we can split with a common denominator, not a common numerator. Okay, I've got it into 2 terms. That's good because I know my answer needs to be in 2 terms. What's the reciprocal of sine? Cosecant. Okay, that's good. We wanted that. What is cosine over sine? Oh, snap, that's what we wanted. So we used 2 identities here. We used a reciprocal and a quotient identity. That's not how you spell that word. Try that again. And voila, there's our proof. And that's really cool because honestly I did it completely different on my notes. So I started with this side. Like I worked the left side of the equation and ended up with the right side. So really, it doesn't matter which one you start with as long as you use correct math things. Last example with me, and then you get to practice on your own. Hee hee. This one's the easy one. Which side's more complicated? The left side. So we're going to be working with the left side here, and we're going to get it to look like the right side. Okay. For this one, I know we could distribute first, but I'm actually going to hang on to the distribution for a little bit just to show you something else, since these are our notes. So the first thing we're going to do on this problem is we're going to change the stuff inside this parentheses using the quotient identities, which means tangent becomes sine of theta over cosine theta, and cotangent becomes cosine of theta over sine of theta. Again, this is not the only way we can do this problem. It's just the way that I think shows one of the steps that I want us to get used to that you may have to use. So that was using the quotient identity. Again, I know you want to distribute that so some things cancel. So just hold on because I want to show you something else, a different way to do it. But you're right. You could distribute that in there because a bunch of stuff's going to cancel. I know you're tempted, but hang on to it. So we're going to keep this cosine out here. We need to be able to add these two fractions together. Because I noticed that my final goal here has no plus or minuses in it, so I need to get these two things to be 1. Which means I need the first term and the second term to have the same denominator. I need their denominator to be sine theta, cosine theta. In that first denominator, it just says cosine theta. So what is it missing? The sine one. So I need to multiply this first fraction by sine on top and bottom, which means that this numerator changes to sine squared, because we're going to multiply what's already there by what the denominator was missing. What does that mean the second one is going to be? Cosine squared theta, because its denominator was missing cosine. So to put a cosine there, I have to multiply the top and bottom by cosine. So this was finding a common denominator. Oh my gosh, I'm so popular today. We can actually add these two things together now. So again, hang on to this cosine in front. I know it's tempting to distribute it in, which you could have done. We're just solving this differently. These are going to be with one fraction, one denominator. Sine of theta over cosine theta. Okay. Is anybody's spidey senses going off for something in that numerator? It equals 1. That's a Pythagorean identity. So cosine of theta over times 1 over sine of theta cosine theta. That's my Pythagorean identity. Now let's distribute, because it's even simpler. When we distribute this cosine, okay, this can be multiplied by 1. That means I'm going to have cosine of theta over sine of theta cosine theta. Because technically this cosine is over 1, and multiplying fractions is top times top, bottom times bottom. That was a good question. And now what you've wanted to do this whole time gets to happen. What's happening here? Yay, goodbye. They cancel. I'm left with 1 over sine of theta from my canceling step. And we check out our goal. Remember, our goal was to get it just to be cosecant. And isn't sine the reciprocal of cosecant? So immediately this can turn into cosecant of theta using that reciprocal identity. And boom, we're done. I love these kinds of problems. I think they're really fun because, again, it's a puzzle, and you and the person next to you can solve them completely differently and correctly, and I think that that's just wildly cool. Yeah, it is.